This is a video using the steady state wellbore simulator USWS to analyze gas condensate loading and to see what kind of gas lift rates we should use to restart the well and to optimize the condensate production from this well. So going to the USWS data file builder, we click on that, and I'm going to open up a file that I have previously built and review that data file. So looking at the PVT data, this PVT data is for a gas condensate PVT. So this is the condensate gas ratio, and the dew point is about 6,589 kPa. Looking at the trajectory of the well, this well is a vertically horizontal well, so it's got a vertical section followed by a bill and then a horizontal section. So this is divided into 10 meters for the vertical section or 20 meters for the horizontal section. In the pipe data, we have two pipes, a liner pipe and a short string pipe. It will display the pipe schematic. This is the pipe schematic. So we have the liner that goes from which goes from 1 to 108, the length of the well, with a short tubing string that goes up to 65. So we would produce from the liner along the horizontal well, the condensate and gas will be accumulated as it flows in along the well, and it will flow up the annulus of the tubing and liner, and eventually the condensate gas condensate will flow up. As pressure drops, we see condensate appearing in the riser section until the pressure drops below dew point, and then we will see condensate throughout, liquid condensate throughout the flowing stream. Eventually, as pressure drops, we would get accumulation of condensate at the toe of the tubing, and that will stop production of the well. We will inject gas down the tubing and lift that condensate back up to the top of the well. So in the liner, we have a 108 segments with a pipe ID of 10 centimeters, roughness perforated along the length of the horizontal well, with initial pressure of 7,000 kPa in the liner, gas saturated, and it only has permeability for the horizontal section of the well. And the short string is open to flow at the last segment. On the 65 is a 4 centimeter ID, and initial pressure 7,000. So the reservoir data, we trying to reproduce the depletion behavior of the reservoir. We don't know how big it is, so we are using as short time intervals of half a day. For each half day, we're going to drop the reservoir pressure by some value. So in this case, we're dropping pressure by 500 kPa, 1,000 kPa, 1,000 kPa, 500, 300 kPa. Sequence of pressure drops, and you can choose whatever you want to, as many points as you wish. This is to reproduce the depletion behavior of the reservoir, and we see that at the dew point pressure 6,000 kPa, below the dew point pressure 6,000 kPa, 5,000 for example, we would have liquid falling out in the reservoir, and that could be mobile depending on the relative permeability curves that we put in, and the corresponding gas saturation. So there's no water fraction in this thing here. This is the relative permeability table that we have used in this particular case. So the production injection diagram, we have one offtake point in the annulus of pipe 1, segment 1, with offtake coefficient, point flow coefficient 100, minimum offtake pressure of 2000 kPa, and maximum offtake rate of 300 E3M3 per day. So 2000 at the wellhead, and reservoir data be going down to about 2200. So we believe that you will see the response, the production of the well as it falls through this range of pressures, and it may or may not be able to produce somewhere around this pressure range here. So that is the data for the gas condensate model, and I previously run the model, but if you were to run the data file, you would go and select that data file, and I call this gas condensate analyst.dat, and you would start the run. But as I have previously run the model, I can go in and click here and get the file name here, open results of the run, and select the two pipes, select the pressure, oil, gas saturation, oil rate flowing into this in the pipe, gas rate flowing in the pipe at all times, and choose my output format for each time, all the pipes and parameters for the entire range of pipe segments, and report that sequence. So initially the pipes are 7000 kPa, and next time we see the rate is 300 E3M3, so it's hit the maximum offtake rate limitation. It's raised the wellhead pressure to 5000 instead of 2000 to meet this restriction. And this is the oil saturation in the segments. This is the gas saturation in the corresponding pipe segments. And you can see that when the pressure is 6000 in the pipe, there is no oil saturation. So this is, if you go from the bottom, from the very end of the horizontal well, we can see that the oil rate is coming in, is increasing as it comes into each segment, is accumulating. Each segment is contributing reservoir input. The rate is increasing as we go along from the toe to the heel of the horizontal well, and there's no liquid. It's mostly gas condensate because it's above the dew point. Once it hits the dew point at about 732, condensate forms in the pipe, and it goes up, increasing as the pressure drops in the pipe, increasing from the dew point to the top of the well. The oil saturation is increasing, so the whole up of liquid is increasing in the pipe. If I go to the next time, this is similar until I go to 0.5 days. So if I go to the third report and look at the reservoir pressure as well, and then you can see that the reservoir pressure is at 0.1 day, the reservoir pressure is 7,000 kPa, and if I go down to 0.6 days, after 0.5 days, the pressure was changed to 6,500, and once the drop in pressure, the pressure in the pipes drop, and previously we had about 731 where the pipe pressure was 6,000, now it's about 761. So the liquid appears in the pipe earlier, and if you go up, it's now more liquid in the pipe at the wellhead. You can go to the next time, until we get 1.1 day, and again we get more liquid in the pipe, and we now have liquid in the pipe all the way along the horizontal well section, and the gas rate is still restricted to 300. Oil rate is 233. Next time, it doesn't meet the limitation anymore of 300, and now it's restricted by the offtake pressure of 2000 kPa. Next time. So as we go through the time, the reservoir pressure drops, oil saturation increases. Next time, until you see the rate is decreasing, the gas rate is decreasing. It's decreasing. So 3.1 days. The reservoir pressure down to 2,500 kPa. Next time, 3.5 days. 3.6 days, once the reservoir pressure drops to 2,200, this well now loads up. It stops flowing. We have a head of liquid buildup from 735 downwards. So this is the head of liquid buildup. And if I display the well schematic and show you the display, show you the pipe schematic, maintain aspect ratio, displayed, say for example, the oil saturation with time, see the oil liquid content in the pipe increasing until 3.5 days, when the liquid condensate loads up, builds up to the bottom of the well, and the well stops flowing. So to get this well to restart, we will inject gas lift gas. We will try two rates. We will try a rate of 100 E3M3 per day and a rate of 20 E3M3 per day. So in this data files, I've created the data file. I'm going to show the data file. In the data file for the 100 E3M3 per day, basically it's the same data file, but in the production injection data, I've introduced a second point at 3.5 days when the well dies. The second point at the short tubing, 7.1, so I'm going to inject gas at the maximum injection pressure of 4,000 kPa and the maximum gas injection of 100 E3M3 per day, and save the file. And so I save it as gas lift 100. I have a similar case where I've done this for 20, and so this one is just 20. So it's the same data, but different gas lift rate. So if I've run these files already, and I can show you the output of the run. So if I go review results, I can go and get the 100 E3M3 case and get the last used report selection and report the results of that run. So I'm going to select the time. I'm going to jump right to 3.5 days, which was the time just before the introduction of the gas lift gas. Next time, so now we're injecting gas lift gas, and we're restricted to the wellhead pressure 4,000 kPa. We cannot inject the 100. We're only injecting 72, and we're returning up the annulus. We're returning 78 E3M3 with a oil rate of 3.6 meter cube per day. The condensate gas condensate rate of that much. So the condensate rate is not significant, and we essentially recycling gas. We are pumping a lot of gas in, but we're simply recycling the gas because the gas condensate well does not require a lot of gas to circulate, to lift. So let's look at the case where we have used the rate of 20 instead of 100 for the gas lift rate. So here we see that the rate is about 3.5. So if we go to the results of the run of 20, and get the last use report selection and look at the time, about 3.5 days, 3.6 days. So at 3.6 days, we're injecting 20, so we made a target of 20. And going down, we can see it goes 20, and we're now producing 27 instead of 3 millicubes per day of condensate. So 3.7 days, 3.8 days. So we're showing that we're getting better condensate recovery by injecting less lift gas. So the knowledge gain is that if we should inject the minimum amount of lift gas necessary to unload the well so that we can maintain the condensate production from the well as much as possible. This is the learning. Thank you for your attention.